The Asen-Schoenberg-Whitney theorem relates the zeros of polynomials and the poles of power series to symmetric functions. I'm not sure we've defined the ring of symmetric functions, so let's look at the basic definitions. Let's call f this function in n variables if it's an element of the ring of polynomials and n variables having integer coefficients. Let's call that a symmetric function. If swapping any two variables so I'm writing xi and xi1 out of order does nothing to the polynomial. So in other words, this is invariant under the action of Sn, where little si swaps variables xi and xi plus 1. So we let capital lambda be the subring of this polynomial ring in n variables of symmetric polynomials. And we know some examples. So constant functions are symmetric, and then we have the elementary symmetric functions, e2, e1, e3. If we've got n variables, they're defined up to en. After that, ed equals 0 for d greater than n, because we can't have a sum of products of d distinct variables if there's only n distinct variables and d is greater than n. And then we have the complete homogeneous symmetric functions. And these are defined for all d. Because these allow repetition of variables. And then we have more natural symmetric functions, which we could define by, let's let PD be the dth power sum symmetric function, and let's let that be a sum of all dth powers of the variables. So P1, P2, P3, etc. are defined for all d. There's no d that's so large that we can't take the dth power of these variables and add them up. And then we had other natural examples. Things like M32, which is a sum of all monomials where we have one variable cubed and another variable squared. The Newton showed that this ring of symmetric functions is isomorphic to the polynomial ring and the elementary symmetric functions. That is, any symmetric function can be written as a sum of products of elementary symmetric functions. So not only sum, let's say z, well, I guess it could be a sum because we could add anything to itself multiple times. Well, a z linear combination of products of elementary symmetric functions. Now there are many formulas expressing different natural symmetric functions in terms of elementary symmetric functions. I want to show you one for the dth power sum symmetric function. I don't remember whose result this is or what the proof is, but I'll show you the formula anyway, just so we get an example of one. So dth power sum symmetric function equals a sum over all partitions lambda of n, sorry, all partitions lambda of d, negative 1 to the a number which I'll call r of lambda d times another number which I'll call c lambda of d, c of lambda d, times the elementary symmetric function e lambda. Where r lambda d equals the length of lambda plus d, and c lambda d equals the number of ways to break the cycle 1 through d into chains of cardinality lambda 1, lambda 2, etc. Going off the board a little bit into chains of length lambda 1, lambda 2, etc. Alright, so let's do this for the fourth power sum symmetric function. So let's make columns for lambda, r, lambda d, c, lambda d, and our cycle is going to be 1, 2, 3, 4. So if lambda is 4, we've got, I'm sorry, this is d equals 4. The length of lambda is 1. 1 plus 4 equals 5. The number of ways to break this cycle into a single chain of length 4 equals 4, because we're just going to break one edge, and then what's left is going to be a chain of length 4. And then if we look at the partition 3, 1, this has got 2 parts. 2 plus 4 equals 6. And then if we want to break that cycle into a chain of length 3 and a chain of length 1, we just pick the one vertex to be a singleton, and then the other 3 are going to be a chain. So we pick one vertex, break both edges incident to it, and we're done. So 4. Choose one vertex and break both incident edges. All right, if we look at the partition 2, 2, then that's got 2 parts. 2 plus 4 equals 6. And if we want to break that cycle into 2 chains of length 2, we pick a pair of opposite edges. If we cut opposite edges, then what's left is 2 chains of length 2. So there's 2 ways to pick a pair of opposite edges. So we'll break a pair of opposite edges. Then for the partition 2, 1, 1, we've got 3 parts. 3 plus 4 equals 7. And then we want to pick any 2 adjacent, well, I guess we could pick one edge not to break. If we pick one edge not to break, that'll give us a chain of length 2 and 2 singletons. So there's 4 ways to do that. And then if we look at the partition 1, 1, 1, 1, that has 4 parts. 4 plus 4 equals 8. And then obviously there's one way to break that into 4 chains of length 1. We just break all edges. So according to this formula, P4 equals -1 to the 5th times 4E4 plus -1 to the 6th times 4E31 plus -1 to the 6th times 2E22 plus -1 to the 7th times 4E211 plus -1 to the 8th times 1E1111, which is -4e to the 4th plus 4e31 minus, minus 1 to the 6th is plus 2e22 minus 4e211 plus e1111. Going off the screen. Minus 4e211 plus e1111. There we go. And I just realized I haven't defined this notation for elementary symmetric functions. We defined e sub k, where k is just one number. When we've got a partition there, we define e lambda to be e lambda 1, e lambda 2, e lambda 3, etc. Just the product. So I could have written this as e2, e1 squared. So E211 equals E2 E1 squared, and that is, say, x1 x2 plus x1 x3 plus x2 x3 if we have three variables times x1 plus x2 plus x3 squared. So again, we can write any symmetric function as a sum of products of elementary symmetric functions. The products we usually abbreviate this way. So E2, E1, E1 is just written E211. And there are formulas relating many natural symmetric functions to elementary symmetric functions, such as this one, which relates power sum symmetric functions to elementary symmetric functions. The end.